Today's topic is all about word equations. This subject I always try to kind of put on a Friday as kind of like a summation of a bunch of stuff that we've been talking about. So what you're going to see represented today, and different things that you should already feel somewhat comfortable with, are things like naming will be important. Other things like balancing chemical reactions will be important, and then also classifying chemical reactions are going to be something that kind of gives us some insight into these. So I think probably the best thing to do is to start with an example and show you the four-step process, or maybe I guess you could say three-step process that we're always going to use anytime we see a word equation and we have to break it down into some sort of balanced chemical reactions with the appropriate symbols. So here's the first one that we'll be starting with. I'll read it to you just in case you can't see it on the screen too well, but it says potassium metal and oxygen gas react to form potassium oxide. So what we're going to do with this is we're going to first come up with the reactants. We're going to put them in the proper symbols. In other words, you're going to take those names and convert them into formulas, right? That's essentially what I'm asking you to do. Second, we're going to do the same with the products, or in this case, just single product. And then once we're all done with that, then we'll balance the reaction. And those are the sequence of steps that we're always going to follow anytime we have to do one of these. So for step one in doing this, we're always going to write the formulas for whatever the reactants are. And keep in mind the reactants are whatever the reaction starts as. So in this case, I'll just kind of highlight them in blue here. We've got potassium metal, and I'll show you what you do with the phase designation there in just a second. And then oxygen gas. Right? And so those two things are the reactants in this reaction. And so we're going to write both of their formulas. And so this part is probably pretty easy, right? The fact that it's just plain old potassium metal, right? It's not in a compound, it's just plain old elemental potassium. Keep in mind that word elemental hopefully will kind of jog some memory cells from earlier in the term. And so potassium is that one of those kind of normal elements that can just exist all by itself. Hint, 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 hint. Oxygen gas can't just exist all by itself, right? So let's get those formulas written down. So potassium metal, we don't have to do too much work other than just finding potassium on the periodic table. But how do I indicate that it's a metal, or that it's in the solid phase? Well, it turns out we're going to put a little phase designation there because there's no information that it's anything but a solid, just like a metal normally would be. We're going to put a plus and then ask ourselves, what is oxygen gas? And once again, that's not a compound, but the trick here is to recognize that oxygen gas, you can't just simply write an oxygen with a G next to it. Right? Turns out that oxygen is one of those magic 7 that we talked about way back early in the term, so far back, like 6 weeks. Whoo, man. That this guy has to be diatomic, remember. Right? And so even when you have kind of simple elements coming together, there's still some like curveballs that chemists throw at you. So, you know, we are going to see a bunch of different examples of where sometimes it's an element, sometimes it's a compound that we have to do some of those naming rules to figure out. We might have to decide whether something's covalent or ionic, right? So all of those kinds of things are going to be types of steps that we're going to have to take over on the reactant side here. And so what we'll add to this reaction is an arrow that just shows you, right, that remember that kind of translates to, in the symbology of chemistry, yields or changes to, or chemically changes to, or reacts to something else, right? So that brings us to step number 2. So obviously, step 2, write formulas for the products. Now you might wonder why I didn't just do this back in step 1. Well, it turns out that there are several reasons why. And so we'll kind of highlight some of those. But one thing that's often true is that sometimes you'll actually have to predict products, right? They'll give you like a reaction type, like what's going to happen on the celebration of knowledge for today, where you may be given a little bit of information, like the fact that it's a double displacement or a combination or one of those other types of reactions that we've seen before. So you may actually have to predict this product based on some of your reactants coming together. Obviously here we're told what this thing turns into, right? Potassium oxide. So potassium oxide is all we have to figure out, but it's not super straightforward, right? Because this potassium oxide, that has a certain sequence of subscripts, right? And we still have to recognize that, that it's a compound, right? So we have to use those compound naming rules. And so one thing that is like a really common mistake when you're doing these kinds of reactions is to try to kind of balance it in your head too early, right? And so what would be incredibly wrong for me to write here is just to simply take these two things together, right? There's a potassium, there's some oxygens, right? Combine them together into KO2. That would be 100% incorrect. I can't do that, right? What kind of the subscripts are here have everything to do with these individual species and nothing to do with what they turn into. And there's a really common mistake among students. I'm going to show you a couple of different examples so that you can kind of avoid that. So blah, 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 right? We go to this potassium oxide. Let's highlight this in a different color. So here is my one product. And I go through, since I recognize that it's a compound made up of two different types of elements or more, I have to say, is there a metal present or ammonium? Right? I'm trying to decide whether this thing is ionic or covalent, so I get the formula right. Turns out potassium is definitely on the metal side of that category, so I know I have something ionic, and I say, oh, Sean said when I have something ionic, I always have to put together a little work area. Right? And so, without going off the screen, hopefully, I am going to have a little work area before I write my answer. And hopefully you can even read this. Ionic side, the ionic always has a positive side and a minus side. And you have to go through and fill in, what is a potassium? That's a K. What is an oxide? Well, that's based on oxygen. Because it's ionic, we know to use that charge table that I've given you previously. You look up the charges and recognize oxygen has a 2 minus and potassium has a 1 plus. At that point, you have to ask yourself the question, just like we did before, is this thing overall electrically balanced? And you would say, no, I need to do something to it. And that something is either the Crossy trick or recognizing the way that I make sure that the plus side of the world, the cationic side of the world, adds up to 2 plus, while this negative anionic side of the world adds up to 2 minus. Right? And so the actual formula that we're going to write here is actually K2O. And you can see that. When you look at that, right, a lot of people get bent out of shape at this point. By the way, we should probably include a phase. It's actually a solid. Most ionics are solid at room temperatures and pressures. You'll notice that the number of Ks do not match, right? And that is totally normal. The number of oxygens do not match, right? What we see here is an opportunity for balancing, right? And so that's what we're going to do. The first step, we're going to figure out the reactants. Then we figure out the products, recognizing that the reactants and products are not really related in terms of subscripts at this point. And then we balance it when we're all said and done. A lot of students balance too early before they actually get these little suckers correct. So what I'll do is I'll erase all this and I'll redraw the reaction as we now know it to be at the top of the board, and we'll go through those balancing steps and then we'll classify it. So here's our unbalanced chemical equation that's been redrawn or rewritten. We know that the left side has to equal the right side, at least in terms of the parts that we end up with. And if you've watched any of the balancing videos, this is the technique that I use, right? You'll notice that I match the Ks with the Ks and the Os with the Os. I go through and account for all the species that are there now. So I see 1 potassium on the left side, and I see 2 oxygens, and then I see 2 potassiums here, and 1 oxygen there. And of course, this is where those that idea of using coefficients comes in, right? Those big giant numbers that go out in front, right? You can't change the subscripts, got to change the coefficients. And this one's a pretty straightforward balance, but I'll just kind of choose to do oxygen first. Put a 2 there. That means that I've now changed both of these numbers. I now have 4 potassiums, and I've successfully balanced my oxygens. I do that iterative process. I come back here and say, okay, how many potassiums do I need? I need a total of 4. Lo and behold, I got that sucker balanced. That is my final answer for the full conversion of a word equation into a balanced chemical reaction. And then if you know about your classifications, you'll notice 2 things coming together to form kind of one new thing, and that is by definition a combination or synthesis, depending on what you want to call it. Combination / synthesis. Okay, let's try one more. Oh, by the way, I can't remember if I said this, but this is directly off your lab, so I just gave you a lab question if you're watching, or a lab answer if you're watching the lecture videos like you're supposed to. Okay, this one's a little bit wordier, and I just kind of made it up. It really has no basis in reality, but you'll at least be able to see all the ins and the outs of kind of doing all the different steps. So we've got copper 1 sulfide reacts with aqueous aluminum bromide, or I should say solid copper 1 sulfide reacts with aqueous aluminum bromide in a double displacement reaction to form an aluminum salt precipitate. And you'd say, what in the hell do all those words mean? That's what the point of going through this is, right? Good news. First thing we're always going to do is we're going to work on the reactants first. We know, because we just saw it, that step 1 is always to figure out what the reactants are. So we know we have solid copper 1 sulfide and aqueous aluminum bromide as my 2 reactants. And so we're going to go through and we're going to do the same exact thing that we do every time we see some sort of name that we need to convert into a formula. I'd say copper 1 sulfide. Is there a metal or an ammonium present? There is. It's copper. Therefore, I'm going to have an area that I split up into the positive and negative side of the world before I do anything else. And I also recognize when I look at the other reactant, aqueous aluminum bromide. Aluminum bromide, does it have a metal or an ammonium present? It has a metal. It is aluminum. Therefore, I have to have another work area to determine what aluminum bromide is. And you can tell how much fun we're all going to have with this. And you go through, same exact thing. You find your charge chart, and you look solid copper 1 sulfide. Well, we know that that 1 corresponds to copper with a 1 plus charge. So there's my Cu1 plus. I know that I've got a sulfide, and I look it up on the table to recognize that there's a 2 minus. I recognize that that's unbalanced, so I got to do a Crossy trick, and when I do that, I'll end up with a formula of C2S, and the fact that it's solid, I'm also going to include that. And let's see if I can fit this other one on there. Same exact process. Find aluminum's charge because we know there's a metal present. We also reminded ourselves that there's a metal present by the fact that I drew this positive and negative box. I know that aluminum has a 3 plus charge, and I know a bromide has a 1 minus charge. So here we'll just do the Crossy trick and we'll kind of go the other direction here. We know after the Crossy trick that I've got aluminum bromide that looks like that. And this is in the aqueous phase. And so just to make sure that I'm always confident in my formula, I show it in my work area. And if nothing else, I get partial credit if something goes wrong. And so I've got my 2 reactants. And notice I can't do anything in terms of the balancing just yet. I can't put coefficients on because I have to go on to step 2 and figure out, well, what the heck did this thing turn into, right? What is the product? I was running out of space on my whiteboard, so I decided to just erase all the kind of non-essential stuff that we've already recorded down here. and we're going to go through and try to figure out what the heck the products of this thing are. So one really big clue is the fact that we have this thing called the double displacement reaction. If you remember, that's the one where you kind of switch dance partners, right? And so anything that was cationic on this side and was paired with an anion, now that cation will be paired with the other anion. And similarly, that aluminum will be paired with sulfur. And so the good news is that little bit of double displacement tells me automatically that I have to put a couple of different work areas in here before I even do my answer. This is also an advantage of showing exactly what's present here in terms of cations and anions, because it helps me to fill out my boxes properly, or to get to the correct formulas. So I know that I started with a copper 1 plus, as long as there's no other scary stuff going on. That charge pretty much gets carried through unless it's a special type of reaction that I am hopefully never going to show you. We know that over on this side is a copper 1 plus. We know that now that little dude needs to pair with a bromine 1 minus. And luckily, the second we do that, we recognize, hey, that guy is nicely balanced. So I already know one of my products here. We look through this reaction, and all we see is aluminum salt precipitate. Keep in mind, precipitate means that's the solid that comes out of a solution. And it doesn't give us any information about what the heck this does. So in a situation like that, usually it's assumed that this thing is just kind of still in solution. So let's just put aqueous next to that thing. And we'll do the same thing with the other side here. We know that aluminum is still going to be a 3 plus. And we know that that sucker needs to combine with S2 minus. We look at that thing, do the old crossy trick, and we recognize Al2S3 should be the formula of that thing. And you'll notice here that it says to form an aluminum salt precipitate. Salt is kind of another word for an ionic compound. So this guy is an ionic compound, and it must be, since it's a precipitate, must be in the solid phase. So we better make sure that we check to make sure everything is balanced in terms of charge. Just to make sure. Yep, okay, so that all looks pretty good. Very next step, I'll erase everything else and redraw it, and we'll balance that sucker, and then we're done. All right, hopefully this isn't too smushed for you. But we have to balance this thing now, and so let's see, it's a little bit bizarre the way I did it here, so let's kind of divide the world like this. We've got a copper, a sulfur, aluminum, and a bromine. Make sure that we've got the matching member over here. There's my sulfur. Is there an aluminum? There's an aluminum. There's a bromine. And we go through and we count up the numbers just like we've done a few times before. We've got 2 coppers, 1 sulfur, 1 aluminum, 3 bromines, 1 copper, 3 sulfurs, 2 aluminums, and 1 bromine. We can start anywhere we want. Let's just kind of pick one. Let's see. I am going to balance aluminum first. See what happens when I do that. So we'll put a 2 there. Now I've changed the number of aluminums, but I've also changed the number of bromines. Okay, so my aluminums are balanced now. Let's look back and let's just kind of go balance bromines now. We'll say, well, I know that I have to have a 6 there, which changes this to 6, and also changes my number of coppers to 6. So far, so good. Might as well balance copper now. Put a 3 there. That changes that to a 6, and that to a 3. And lo and behold, I think we've got a balanced chemical reaction. We already know that it's a double displacement because it was told to us in the question. So here's my nice balanced chemical reaction. Hopefully that's a little bit easier for you now that you've seen this video. We're going to do one more example, and I'll just kind of throw a bunch of stuff at you with polyatomic ions, and we'll kind of just real quickly go through the process. Our final example here for a little while, aqueous sodium sulfate solution, 8, reacts with aqueous barium iodide to give an insoluble barium salt. So let's just kind of tackle things one at a time. First, we need to do step 1. We need to figure out what the formulas are for our different reactants. Our reactants are aqueous sodium sulfate and aqueous barium iodide. And so we go through, is there a metal present? Heck yeah! So we know we have something that's ionic. And that other thing, barium is also a metal. So we've got 2 work areas divided into the plus and minus side. We look at our charge sheet, we say sodium, we know what that is. That's a sodium 1 plus. Now, this is where knowing how to name polyatomics comes in really handy. That ATE or ITE ending should kind of trigger your brain to look at your polyatomic list. If it's not an IDE, you should be pretty suspicious that you have to look at the polyatomic ion list. Turns out, when we look that up, sulfate is an SO4 2-, which gives rise to our little crossy trick. And we recognize that aqueous sodium sulfate looks like that. And let's make sure that everything is balanced after we see what the formula is, and it does look pretty good. Same kind of thing for barium iodide. You look for the charges. Barium is a 2+, iodine is a 1-. Do your crossy trick. You end up with barium iodide looking like that. Let's check. Looks nice and balanced to me. Time for step 2. Looking at this, you'll recognize that it doesn't give us too much interesting information other than the fact that it's a barium salt. So you might say, well, what gives? Well, it turns out anytime you've got kind of 2 things dancing together with another 2 things dancing together and no other information, usually that's a double displacement. And so let's assume that's the case, and in fact it is. And so this being a double displacement, we know that the 2 things that are going to form are both ionics. And that's even on the screen. And so let's go through. It says insoluble barium salt. So let's do the barium salt first. A barium 2+ must have come together with an SO4 2-. And so the good news is that that thing is balanced as is. And it says it's insoluble. Therefore, you know that it must be in the solid phase. And the other part is a sodium 1+, which must be now paired with an iodide. That one also is written exactly like it should be. And I'll redraw it anyway. And then we'll balance it. All right, so we've got that all balanced out. We could, of course, write this down on a piece of paper and go through the balancing. But the good news is, if you recognize there's 2 sodiums and 2 iodides and everything else is pretty balanced, we can just do that. And there we go. We've got a balanced chemical reaction. So at this point, what I'd really highly recommend you do, if you're not too sick of doing this stuff just yet, is go to your lab, try a couple of the word equations there. Some of them are a little bit funky and you might need to ask about in office hours. Have fun.